things. Actually, we really have three separate things going on this week. Some of this, well, it's a lot of it's for all of y'all actually. So today at noon, I sent announcements out about this, and I'm sure that you've heard this from, especially chem majors. But at noon, we're having a special welcome bath lunch for the NCSS. That's the chem club. So you guys come out. We'll be right out here in the quad. There'll be food. That's right. What type of food is there? Y'all know?
They're bringing vegetables.
We're just having vegetables for lunch. No, we'll have other stuff, right?
They said bring food trade.
Oh, okay, sandwiches and all. So be more than just vegetables. So anyway, come out. It's at noon. So you can just come after your class, which ends at quarter of noon or so. And then also, there's a special talk. It's in this room tomorrow at 4 o'clock. And then also there's a lunch, which is over in the conference room at 12:30. So the lunch is in the room right opposite here, the conference room, which is next to the computer lab. So that's what Rebecca Adams, I told you about Rebecca. She's really awesome. Good student, graduated from here a number of years ago. But you know, she's about our age. She's probably upper 20s or so. Our age. Anyway, y'all have a good weekend? Yeah? Alright, if you have any questions about either of these, let me know. I think if you're going to go with Rebecca at lunch, you need to sort of give us a heads up. So, is that right? Cyrus, an RSVP sort of to Dr. Cortez? Or you can tell me as well if you want to go. I encourage you to go. It'll be really good. Those opportunities to talk to people that have done things really help you to form a perspective and sort of figure out where you're going to go when you graduate. All right? All right. There's something else. Yeah, so three things. Lunch at noon today, lunch tomorrow at 12:30 with Rebecca, and then the talk at 4 o'clock here in this room tomorrow. I have to let you out a few minutes early today, so I have a meeting back campus at 7:30, so about 7:22 or so I'll let you out, if that's okay. Is that all right? Yeah, okay. It'll be okay. We're going to be all right. Let's see. This is my job. This is true. Everybody had a good weekend then? Was there any big news? Hillary, did you finish your book? Good. And you still went to the parade with Bren?
No. She never called.
She was reading her book. I remember before we had kids, like weekends, I would spend the entire weekend. I'd go in Friday night and have like a stack of books, and then just wouldn't come out until Monday morning. And those were nice weekends. I sort of miss them. My wife was the same. All right, so our test is in 2 weeks, and we're going to see some circuits on there. We'll see some capacitor circuits. We're going to do some today for practice. Many of you have already seen capacitors, resistors in series and parallel, and you'll find that capacitors in parallel and in series are very similar, but they're a little bit different. Let's see, I'll write out the rules for capacitors, and then I'm going to write out the rules for capacitors and resistors a little bit later. So if you're familiar with the rules for resistors, you can just sort of see them laid out side by side. But let's do capacitors in parallel first. Capacitors in parallel, when I hook them up in a circuit, they look like this. So I have my power supply, or my battery, and then I have a capacitor. Remember those symbols that I showed you last time? Look like this. This is my power supply, this is my capacitor C1, this is my capacitor C2. Now this one I think is probably fairly obvious that these are in parallel. They run in parallel like this, but really the way that you tell that capacitors are in parallel, and I think it might be obvious, it might not be obvious. You know that they're in parallel because I see a junction right here. And while that might be obvious in this case, we'll see some circuits later, like what you'll have on your exam. It won't be obvious on those. So when you're looking for capacitors or resistors in parallel, you look for a junction. And a junction where one wire splits into two wires, or one wire splits into three wires, signifies to you that there is a parallel circuit beginning at that point. Like I said, not terribly important here because you can identify them just by noticing them, but when we get to more complicated circuits, it will be important to identify those junctions. So capacitors in parallel, when they're in parallel, they have the same potential or voltage across them. So if the capacitors have different, if the two capacitors are different, then they have different charges stored within them. And we talked about the charge that's stored on a capacitor. That's this Q is equal to the capacitance times the voltage. Let me go back. We haven't done series yet, but let me just show you something as well. I can have what we call a combination circuit, where if I have a capacitor like that, and then say two capacitors like this. In this case, I have one capacitor that is what we say in series. It's in series with two other capacitors that are in parallel. And notice that I can identify these two capacitors because of that junction where one wire splits into two. All right. Again, not terribly important here because you probably just recognize it, but when we get to more complicated circuits, it will be important to identify those parallel junctions. Okay, so when electrical devices are connected in parallel, let's see, did I do a picture? No. When they're connected in parallel, you can sort of think of them like this. So I have my battery, it's 12 volts, it has its two terminals, and I hook up a capacitor to it. That capacitor is going to have a voltage of 12 volts. But I can come along, I can hook up another capacitor like this. These are also in parallel. That one also has 12 volts. So when you imagine any electrical device being hooked up in parallel, you can imagine that it's being hooked up individually to the battery, and so whatever power or whatever voltage is supplied by the battery, each device gets that voltage. So that comes to our first rule, is that capacitors in parallel have the same voltage. We'll see that there are about 6 different rules, and that's one of them for capacitors in parallel. There are like 3 rules for each, parallel and series. Capacitors in parallel have the same voltage. So each of the capacitors in parallel experiences the full 12 volts. So here, for example, what is the charge on C1 and C2? Well, what is the voltage on C1 in this circuit? It's 10 volts, because it's hooked up in parallel to a 10 volt power supply. So I have 10 volts of voltage on this capacitor C1. Likewise, I have 10 volts on here. So the voltage on each capacitor is 10 volts. And notice that if I ever have two quantities for a capacitor, since Q is equal to CV, if I have two quantities, then I can determine what is the third. And so this will be sort of one of our rules as well for capacitors in parallel, also for series, that Q is equal to CV. If I know any two quantities for that capacitor, then I can determine the third. If you're in the lab, you've seen Ohm's law, and I like to sort of think of this as the Ohm's law for capacitors. So if I want to know Q1, it's C1 times V. So that's going to be 1 microfarad times 10 volts. Notice I didn't change my capacitance to farads, although that is the SI unit. I can just carry that micro over, and I get 10 microcoulombs. That is the amount of charge that's stored on that capacitor. I have plus 10 microcoulombs over on this side. On this side, I have minus 10 microcoulombs. Or we don't have 0 microcoulombs, we don't have 20 microcoulombs. I have 10 microcoulombs of charge stored on each plate of that capacitor. Just one side's positive, one side's negative. And then for Q2, what is the charge on that one, on C2? It's going to be 20 microcoulombs. So C2, V2, 2 microfarads. It's a bigger capacitor, but the same voltage. So it has a bigger capacity to store charge. So with the same voltage, it will store a bigger charge. All right, hopefully that's easy, but we will get some more complicated circuits. Is that easy so far? Yeah? All right. All right, so two or more capacitors also can be replaced by a single capacitor that will have the same capacitance as the multiple capacitors in the circuit. So if I have two capacitors, there is a capacitance that is equivalent to those two capacitors. That electrically, to a charge coming along in the circuit, it looks identical. And this is called the equivalent capacitance. It'll be a pretty important concept as we move into this chapter, and then also the chapter on resistive circuits with resistors, and then later we'll put them together, resistors and capacitors. All right, so the equivalent capacitance is just this idea that I can replace two or more capacitors with an identical capacitor. At least it looks identical to the electrical circuit. For capacitors in parallel, the equivalent capacitance looks like this. It's C1 plus C2 plus C3 plus however many capacitors you have. So I have here C1 is 1 microfarad, C2 is 2 microfarads. So the equivalent then is equal to 1 plus 2. That's 3 microfarads. All right. This is our third rule. So now for caps in parallel, we have three rules. We have 1, they have the same voltage. 2, I'm going to give the equivalent here. The equivalent is equal to C1 plus C2 plus however many capacitors you have in parallel. And then the third rule is that Q is equal to CV. All right. There is a fourth rule, and I'm going to go ahead and sort of write it, but it's not really one that we use. I'm going to write it in a different color. I'm only writing it because we'll see a similar rule for resistors, and I find it's helpful just to sort of see them all laid out in parallel. So the fourth rule is that the equivalent charge is equal to the sum of the individual charges. I'll work that out in this example and show you how that's the case. So here, let's say that I have 10 volts here. That means I have 20 microcoulombs here. Q equals CV. C is 2 microfarads times 10 volts. That's 20 microcoulombs. Here I have 10 microcoulombs here. So those are our individual charges, Q1 and Q2. But over here on the equivalent capacitor, I have 30 microcoulombs. Not really a rule that we use, but it's true. But we will use it when we get to resistors in parallel. There will be a very similar rule that has to do with the current, which we call the junction rule, where the total current will equal the sum of the individual currents. So to sort of be aware that this is here, but we're not going to use it for dealing with our capacitor circuits. And once you get these rules, all you need to know are these three little rules, and capacitors really just become an application of these rules as we deal with the circuits. It's kind of like a little puzzle. Let's try this quick test. This is one of our easier circuits. Let's try it out. Y'all go ahead and do it. Let me pull up the clicker base. What is the charge on the 3 millifarad capacitor? All right, sorry about that. Should have done that beforehand. But what is the charge on this capacitor? What is that charge? All right, so a few more seconds. I'm going to stop at 20. Stop at 20. Okay, there we go. Awesome. Hey, check y'all out. All right, so these are pretty straightforward. You might have one in the multiple choice, but probably, maybe not, probably not. All right. All right, it'll be worth 30 points on the test. Yeah. All right, no. So here, all of these have 18 volts, 18 volts, 18 volts, 18 volts. This capacitor then, Q is equal to CV, 3 millifarads times 18 volts, and 3 times 18 is 54. All right? But easy problem, but still worth a joke, right? Or it's not even a joke, it's really a tragic story. Because at Thibodeau Elementary yesterday, I'm sorry, I shouldn't even call it a joke because it's tragic. There was a kidnapping at Thibodeau Elementary. Did y'all hear about this? It was in the paper this morning. He woke up. Seriously? Like, that's good. That was good. No sense of humor, you people. All right, let's look at capacitors in series. Capacitors in series are a little bit more difficult. All right, for capacitors in series, now let me just sort of lay out their rules. All right, capacitors in series have the same charge. I'll write these again, but I just want to lay them out here. For capacitors in series, the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus ... Capacitors in series, Q equals CV. And then also for capacitors in series, the total voltage is equal to V1 plus V2 plus V3 plus however many capacitors you have in series. We will use all four of these rules. Remember, for capacitors in parallel, there was a fourth rule that we didn't really use, but for capacitors in series, we'll use this rule a lot. So capacitors in series all have the same charge. Remember, what kind of charging is this? Is this charging by conduction or induction when I have capacitors set up like this? Conduction or induction, particularly in this middle part. Let me give you a hint. Look, there's nothing touching here. So this is charging by induction. Now when I put a charge on this first plate, all the other plates sort of fill in. Because I put plus Q here, and then the negative Q rushes over without any touching, any contact, and then I get a distribution of charge. That's an example of charging by induction. Circuit, we would write like this. These are in series with one another, and you can have, any number of capacitors in series. The equivalent is given as 1 over C1 plus 1 over C2. It's a C right there. Plus however many capacitors you have. Now, on your equation sheet, it's written a little bit differently. Let me write it as it's on your equation sheet. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus ... These are identical statements. I'm just taking the inverse of this in order to get this statement. So this is on your equation sheet, but this, in practice, this is more what we're going to use. All right, so let's say, for example, I have a 3 and a 6 microfarad capacitor, and I want to know what the equivalent is. I say 1 over 3 plus 1 over 6. Let me do it. I'll do it right here. It's fine. You can do it wherever you want. That's equal to 1 over 2/6 plus 1/6. That's equal to 1 over 3/6, which is a half. 1 over a half is equal to 2. So this equivalent is 2 microfarads. Listen, there are some common fractions that I like to use. And so you can use your calculator for these things, but I find that the more you use your calculator, the more you're going to make mistakes because, you hit a button incorrectly or whatever. So it'll benefit you to just sort of get a feel for the numbers that I use in the circuits because you'll just be able to see, oh, there's a 3 and a 6 microfarad capacitor in series. The equivalent of that is 2. Let me give you some of those. So, for example, if I have a 3 and a 6, that gives me 2. If I have a 4 and a 4, what is that? 1 over a quarter plus a quarter, that's 1 over a half. That gives me 2. If I have a 3, and a 3, that gives me 1 over a third plus a third plus a third. That gives me a 1. If I have a 5 and a 5, is that right? Or a 5 and a 10? 10 and a 10? 10 and a 10. 1 over a tenth plus a tenth, that's 2 tenths, that's 5. There are some others, and you'll see them as we go through, but you'll see combinations of numbers that fit together to give you nice round numbers. Now, that's not always the case. Sometimes you'll just have to put them in your calculator and figure it out, but it'll help you or benefit you to just recognize those combinations. Listen, we got a couple of chapters of circuits, so you're going to recognize them for sure, because we'll see them a lot as we go through. Okay? Y'all don't look very excited. Circuits are kind of fun. Circuits are like a little puzzle that you have to put together. And you know, what class, tell me, what class do you get to come into and do puzzles for like 55 minutes? Organic 2. Besides Organic 2. Like, those are really hard puzzles, but these are just like 2-star puzzles, right? I did not like Organic at all. It was like black magic. I did not understand it at all. So I really applaud y'all that take and enjoy Organic. And I know it's difficult, but I know that many of you do enjoy it because it's difficult, maybe. All right? So, I give the rule about they have the same charge. Yeah, capacitors in series have the same charge. There's the equivalent. Listen, if I have an equivalent capacitor, let's say that I have 12 volts here, that means that my charge on this capacitor, Q equals CV, that's our third rule, by the way, is going to be equal to 2 times 12, or 24 microcoulombs. So that means that I have 24 microcoulombs here and 24 microcoulombs here. Because do capacitors in series have the same charge or the same voltage? Which is it? Capacitors in series have the same charge. Capacitors in parallel have the same voltage, right? Series have the same charge. Capacitors in parallel have the same voltage. Fortunately, that's sort of the same for resistors too, except we replace charge with current. So, notice that the charges are the same. Also notice that now that I know Q and C, I can find the voltage. So what is this voltage? Well, Q is 24. C is 3. So V is Q divided by C. That's 24 divided by 3, which is equal to 8 volts. I could do a similar thing. This is V1. I could also find V2. I'll take just a moment and find V2. And write it down or work it out in your head or whatever. What is V2? It's 4 volts, right. 24 divided by 6. 24 microcoulombs, that's my charge, divided by 6 microfarads, that's my capacitance, gives me a voltage of 4 volts. Oh, but you say, this was 12 volts. Notice that this was 8 volts, and this is 4 volts. What is 8 plus 4? Is 12. So that gives us our, what was that, our fourth rule, I think, for capacitors in parallel. That the voltages for capacitors in parallel will add up to give the total voltage. Let me add a little thing to that. I'm going to go back up a page. I'll write it down here. So, also, remember we drew this combination circuit earlier? Also, whatever voltage I have across these two capacitors, I will also have across those capacitors. We'll see that in circuit, so if it doesn't jive with you right now, that's okay, but we'll see that. That rule, that capacitors in parallel have the same voltage, also applies if the parallel branch is embedded within a larger circuit. It'll be a pretty useful characteristic of these circuits. Okay, so let's do this example. This one's a little bit more difficult, but not a lot more difficult. I'm going to give you a couple minutes. I want you to tell me what is the potential difference across these, and what you need to do is you need to find the equivalent capacitance and then determine what is the charge on the equivalent capacitance. Capacitors in series have the same charge, so whatever charge is here is also here and here. Once you find those charges, you can calculate the voltages. Now these numbers don't work out evenly. But no, wait, stop. Let's make them, we'll use that 3 and 6 combination instead so that the numbers work out more readily. So we'll do 3 and 6 microfarads instead of 2 and 4. But go through all the steps, because by now some of you might actually be able to look at it and not do any of those steps and just tell me what the voltages are if you're an astute observer of how these things relate to one another. First, find the equivalent capacitance. 1 over 1 over business. Then find the equivalent charge. Then find the voltage on each individual circuit. I'm going to start filling in some of these things. You just go ahead and finish it up. I think probably gotten this far. All right, so a couple of things here. This is our equivalent capacitance. 3 and a 6 in series is 2 microfarads. The equivalent circuit, then I can just replace these 2 capacitors with this 2 microfarad capacitor. And I know that that 2 microfarad capacitor has 8 volts across it. Because, you know, it's the only one in that circuit. And so it has to have 8 volts across it. And so the equivalent charge is going to be C equivalent times the voltage across that, which is going to be 16 microcoulombs. But because of my rules, capacitors in series have the same charge. This is 16 microcoulombs, and this is 16 microcoulombs. Now that I know those two quantities for each capacitor, I can determine what is the voltage across each capacitor. For this one, it's going to be V is Q1 divided by C1, and Q2 divided by C2. So C1 was 3 microfarads. This was 16. So that's 16/3 volts. And then Q2 was 6 microfarads, so that's 16 over 6. That is going to be 8/3 volts. Notice we can check this. We can say, well, 16/3 plus 8/3, that's 24/3. That's equal to 8 volts. So notice that our voltages do add up to give us the voltage across the battery. Also note that C1 it does half the capacitance of C2. has twice the voltage. So Q is CV. Recognize this inverse relationship between C and V, that if C goes up, V goes down for a given charge, and vice versa. If C goes down, V goes up. There's an inverse relationship. Now, when we get to resistors, and some of you know that if I increase the resistance for a given current, I increase the voltage. And so this is a little bit different than it is for resistors. Okay. Now, also, when electrical devices are in series, as I said, the sum of their potentials is equal to the total potential. All right, go down from here. Try this quick test. You tell me what is the potential across the 24 microfarad capacitor. You could probably look at this and hone in on the correct answer without even putting your pen to the paper. But in fact, before you work it out, think of these. Which answers can you get rid of right away, and which do you think is the most likely answer, given that I'm looking for the voltage across the 24 microfarad capacitor? Are there one or more answers you can get rid of automatically? There are. There are, in fact, two answers that you can get rid of automatically. So think about that first, and then find the equivalent capacitance, find the equivalent charge. That charge will be on each capacitor, and then you can find the voltage on any one of the capacitors, because you'll know the charge and the capacitance of each. You're probably not going to be able to do this. You might be able to do it without the calculator. While you're doing that one, I'm going to write another problem up here. If you finish this one, you can think about this one. We're doing the one right here, right now, but after this one, we'll work this next one. Should have think about it, but try to work the second one without actually writing anything. All right, let's stop in about 10 or 15 seconds. Doing pretty well. Many of you have the right answer. We'll stop at 320, 322. Okay, good. C is right. So you first find the equivalent capacitance. CEQ is 1 over, all that business. 1 over 3 plus 1 over 6 plus 1 over 12 plus 1 over 24. What is that value equal to? So, what is it? 0.16? 1.6. 1.6 microfarads. Hey, I want you to notice, we'll see this with the resistors. It'll make more sense with the resistors. But I want you to notice that this capacitor is smaller than any one of these capacitors. In fact, when you have capacitors in series, your capacitance is limited by the smallest capacitor. That sort of makes sense, right? Because you imagine you're putting charge on this capacitor, it can only hold so much charge, and then whatever charge you put here is distributed all the way throughout. And so even if these guys can hold more, this guy can't hold more than that, or gal, although, you know, they're capacitors. But anyway, they all have the same charge, and so we're limited by the one that can hold the least charge. All right, once we find that equivalent capacitance, we find the equivalent charge, which is 1.6 times 18, and that is, I don't know, what is it? 28.8 microcoulombs, and then that is 28.8 microcoulombs on this capacitor. We can find the voltage is what V is, what is it? Q divided by C from our Q equals CV relationship. All right? Let me ask you another question. You think a kangaroo can jump higher than the Empire State Building? What do you think? No? Is that what you think? That's what you're thinking, right? Of course he can. The Empire State Building can't jump. All right, let's try this next one. Here we have a 3 and a 6 with 24 volts, and I want to know what is the voltage on the 6 microfarad capacitor. Now, don't find the equivalent, though. I mean, you know in your mind what it is. But what is, well, to make it more complicated, let's say instead of 3 and 6, let's say that it's 5 and 10. So what is the voltage on the 10 microfarad capacitor? There's a way to look at this and think about it such that you don't have to determine the equivalent capacitance. You don't have to do any of that business. You can think about how the voltages are distributed across those capacitors. Because I know that my voltages across the capacitors have to add up to equal to 24, right? I'm going to have two numbers that add up to 24. And I know that one of the capacitors will have a bigger voltage than the other. Which one has the bigger voltage? I always forget. Is it the 5 or the 10? The small one has the big voltage, or the big one has the big voltage? The small one has the big voltage, because there's an inverse relationship between C and V. One goes up, the other goes down, holding Q constant. So this one will have a smaller voltage than this one. By what factor will its voltage be smaller? By a factor of 2, or a half, right? So this one I have half the voltage of this one. And so with that, I'm looking for two numbers that add up equal to 24, one of which is half that of the other. And then you think, well, gosh, what numbers add up equal to 24? I don't know, 12 and 12 add up equal to 24? That doesn't work. 11 and 3? That doesn't work. Okay, you see what I'm talking about? You can think about how the voltages are distributed. All right, let's stop this in this business at 205. 205. Hey, check it out. B is right. It has 8 volts on my 10 microfarad capacitor. 8 volts there. And then I'll have 16 volts there because I have twice the voltage. All right? What do computers eat for a snack? Microchips. All right, let's try some you're not really going to see pure series or parallel. You might see one in the multiple choice, but on your test, you're going to see combination circuits. And we'll do some simpler ones first, and then we'll do some like you'll see in your test. All right. So usually our circuits have multiple things going on. They have some series and some parallel. So let's take this circuit, for example. I want to know what is the charge and voltage for each capacitor. I have a couple things going on. I have parallel right here because I see my junction, and that junction tells me I'm splitting into two parallel branches. But in one of these parallel branches, I have capacitors that are in series. And so I want to first figure out what is the equivalent capacitance in each for the circuit. So to find the equivalent capacitance here, I start with the smallest section that is either purely series or purely parallel. In this case, the section that is what? Is it purely series or parallel, the section we'll start with? It's series, right? I'm going to start with this section because notice there are no parallel parts of that section. And so the equivalent of that, a 4 and a 4, is 2 microfarads. So I have 2 microfarads, I have 1 microfarad, and I have 12 volts. Now I find the equivalent of that. Well, for capacitors in parallel, it's just 1 plus 2 equals 3. So that's going to be 3 microfarads is the equivalent with 12 volts. And now, listen, sometimes students don't write out their circuits. But whenever I'm working through circuits, I always write them out as I go through the steps. Because once I get to this step, I can work backwards and get back to where I was. So now I can figure out, well, Q is equal to 3 times 12, C times V, are 36 microcoulombs. Although I didn't really need that, did I? So I know here that I have 12 volts here, and I have 12 volts here. That means that I have 12 volts on this capacitor, and the charge on this is 12 microcoulombs. Q is equal to C times V. And then up here, I know that on these two capacitors, I have 12 volts. So what is going to be my voltage on this left capacitor? It's going to be 6. I know that it's 6 because these are two identical capacitors, and so it's going to split that 12 volts evenly. Capacitors in series split voltages. Capacitors in parallel share the same voltage. Capacitors in series split them up. Capacitors in parallel will share the same voltage. So I got 6 volts and 6 volts on these two. And then I also have 24 microcoulombs, 6 times 4, 24 microcoulombs, 6 times 4. Okay? So on your test, I'll give you a circuit. It'll probably have a dozen capacitors in it or so, 7, 8 capacitors. And you have to find the charge and the voltage on each. And we'll do a couple in class, and there's some in your homework. There's some on every test that I've ever given, so you have lots of different practice ones. Let me recap the rules for you. How many times can I use that fun before it? Have I used it yet with y'all? 3 more times maybe? And then it will no longer become funny? It wasn't funny this time? Yeah, all right. So our rules, and in fact, I'm going to do it for resistors too, because many of you have seen resistors. And I think it's helpful to just sort of see it laid out. For capacitors in series, or in, what do we do first? In parallel, we have these rules. 1, they have the same voltage. 2, the equivalent equals C1 plus C2. 3, Q is equal to CV. And 4, which we don't really use, but I'm going to list it anyway, that the equivalent charge is equal to Q1 plus Q2 plus ... All right. For capacitors in series, a similar set of rules. capacitors in series have the same charge. Capacitors in series, the equivalent is that funky 1 over business. For capacitors in series, Q equals CV. And for capacitors in series, the voltage on the equivalent is equal to the sum of the individual voltages. So like, for example, I had 12 volts here. That doesn't work. Sorry, I had 12 volts here. This is the equivalent. So these two add up equal to 12. Now let's see resistors in series and parallel. And some of you might not have seen this, and that's okay. Just write it down, and we'll sort of see it again next chapter. Resistors in parallel, they have the same voltage. That's the same. 2, the equivalent is equal to that 1 over business, 1 over C1 plus 1 over C2 plus ... Notice that that's switched, so I'm going to put a little star right here. It's switched what we saw for capacitors. 3, V is equal to IR. And then 4, I total equals I1 plus I2 plus ... Now while we're not going to use this one, we'll use this rule quite a bit. And that's why I showed you that 4th rule for capacitors, just so we can have them all parallel to one another, all these rules. And then for resistors in series, the rules are very similar except for the equivalent capacitance and equivalent resistance. 1, they have the same current. Current is the flow of charge. So whereas we're talking about charge here, we're talking about charge over time here. So you can sort of think of charge and current in a similar fashion. If it helps you to put them together in your mind that way, it does me. The second one, this one's a little different. The equivalent is equal to C1 plus C2. The third is V equals IR. That's our Ohm's law. And then 4, what was the 4th one? Oh, it's the same. I'm sorry. The V equivalent is equal to V1 plus V2 plus V3. So notice that these rules are basically all the same with the exception of the equivalent capacitances. They are identical. All you have to do is, where you have Q at one point, you put I instead. But Q and I are closely related. So the rules work out to be very, very similar for capacitors and resistors. We'll see these again, and I'll probably lay them out for you again side by side like this later. Let's see. We have a few more minutes, so let's see what's on the next page. Okay, let's look at this. I think we have enough time at least to find the equivalent capacitance. So I want to find the equivalent capacitance for this circuit. And again, it helps me, and I'll do this when I work it out, to draw the subsequent circuits. So as I find the equivalent of the first part, which in this case is going to be this one right here, then you can redraw that circuit as you go through. So find the equivalent here. I'm going to take the screen away for just a minute. You'll be finding the equivalent capacitance.